I have for your consideration the suggested implementation of curriculum from the Concord Consortium in my classroom. Over the course of this presentation, you can expect to see an overview of the curriculum, which will include the materials provided, so I'll look at the online materials and what things you can print, evidence of connection to next generation science standards and the Nebraska State Science Standards, evidence of the quality of the curriculum via an EQUIP rubric, and the neuroscience back practices that you can find evident in this curriculum. I'll also give a brief summary of classroom implementation, where I will go over what things from this curriculum are already present in my classroom and how my instruction would need to change to implement this curriculum. We are going to be discussing a set of units for physical science, which are titled Interactions. They are a collaboration between the Create for STEM Institute out of Michigan State University and the Concord Consortium. They are by no means the only units that are provided by the Concord Consortium, but they are the ones that I'm the most interested in due to them being physical science and that being the class that I am teaching. While the materials I'm going to display to you online are available online and digitally, it's worth noting that they can also be printed. So if you have students who don't have access to technology or who struggle to read online or maybe don't test very well when they're tested digitally, you could print these materials for them. And as an added bonus, all of these materials are publicly available free of charge, which is wonderful. The Concord Consortium states at the beginning of their Interactions unit that the Interactions curriculum introduces students to science as an endeavor, a process we engage in rather than solely a set of discoveries by others. Through engaging in modeling and scientific explanation, students explore curious aspects of the everyday world, discovering how the unseen world of atomic-level interactions and energy transformations are responsible for much of what we observe around us. Now, I'm going to walk you through some of their materials to show you how they go about putting that in action. So this is the landing page. You can see that quote up here that we just went over, and down at the bottom are all of the units available for this curriculum. You can see they split their units into several parts most of the time. And when you click this little plus sign over here, you can see the pre and post tests for this particular unit and the investigations, which is what they call essentially their chapters. You can assign these if you're going to have your students create their own account on the Concord Consortium, or if you would rather do this through Google Classroom, you can share the link out to them. And then you can access the teacher's guide, and if you click this little more button here, you can see which standards are covered in this particular investigation. So let's go ahead and take a look at that teacher's guide. The first page here takes your investigation and your driving question for it and breaks it down into the different activities you'll do throughout the lesson and shows you what their driving questions are and then a sort of synopsis of the things that you're going to have students actually do and look at. They then have an overview for the entire investigation where they show you what performance expectations are covered again, and then they actually break it down by disciplinary core idea, cross-cutting concept, and science and engineering practice, not only showing you which ones associated with this performance expectation are covered, but how the investigation builds towards those things. And then not only do they do that for the overall unit, but when you start each activity, they also break down the disciplinary core ideas, cross-cutting concepts, and science and engineering practices for that activity. And then they will walk you through in great detail the activity that you're going to have students do. So in-class readings that you're going to do, outlines of activities, questions you can ask to probe students to think deeper about things. They show you what students are going to see in their perspective. And this right here, this first activity is very discussion driven, but as you get into more lab-based activities, they show you what those students are supposed to be doing as well. So you can see, we'll scroll down here quite a ways to get to the actual next activity. Here's 1.2, which has students do an investigation using some clear tape, and they show you what it should look like for students to do this. And this also is something that students will see on their end of things if they're accessing these materials digitally. But you can see lots of detail, sample student responses, things you can clarify, essentially what they are expecting or hoping students to see and formulate and think about during these activities. So excellent teacher materials. This is what the Concord Consortium looks like from the teacher side if you are signed into an account and looking at your classes. So if you created a class on here to have students join, then this is what it would look like. I created one using a student created with another one of my accounts so that I could take a look at what things look like behind the scene. So if you want to see what this looks like for students, you click the preview. It'll show you what they're going to see on their screen. If you click class dashboard, it brings you here. And I only have one student in this class, but if you had more, you'd have a whole list of students down this side. And so you click on it, you say, I want to take a look at question 3. It'll tell you the question. And then when you click on this, it shows you how each individual student responded to it. So you can take a look and really see how students are doing. And this is available the entire time students are working on this. So you can sort it by most progress, least progress, who's farthest along, who hasn't gotten very far yet, and just see how students are doing. So this is available the whole time that students are working on this. Once you have shut it off, closed it, you can then click on report, and you can come here and you can actually give students feedback for their questions. All right, close out of that. From the student side of things, okay, this is what it looks like for them. So pretty similar. You can see here, I don't see this in my dashboard because I assigned it, but no one has started it yet. So I don't see it in my dashboard yet. We're going to take just a quick look in here so you can see what some of these things look like. Because this is the first unit, they have a little video about how to use the drawing tool because they're going to ask students to create models. They have an image and a scenario, and then they ask students to think and write about it and justify their predictions about what's going to happen. So right here, we are introducing a topic in an interesting way, previewing it for students. We're also asking them to access prior knowledge. Maybe they know about positive and negative charges repelling each other. Maybe they want to talk about that already. So this is just the pre-assessment, but already we can see some of the expectations that students are going to have. They're going to be expected to know about this at the end, so we're previewing it for them. And then they show video content. So this is an interesting here, using a Van der Graaf machine to cause the wig to stand on end so students can watch this video and see it. This would be nice if you didn't actually have one of these in your classroom that you could show students. And then they want students to draw several different models, one before it turns on, one when it's starting to get warmed up, and then one at the end when all of the hair is sticking out. And when you open this, not only do they want you to draw it, but they also want you to explain what's going on. And they have lots of great tools for students to use, from drawing tools to specific lines, arrows. You can select these stamps and have a variety of tools just to make it easier for students to visualize what they are talking about. So you've got that there for them. And then, of course, as you go further on, for example, if I run this one, there are some simulations that you can run as well so that students can experience things at the macro scale or micro scale that they couldn't experience in a lab. So they can run these simulations in here too. And I don't know if you caught this, but you can run this for an individual student, or if you want your students to work in lab groups or with partners, you can have them run it with other students as well. All right. To summarize what we just looked at, on the site, teachers can set up an account. They can use a Google account if they desire. They can view and print materials. They can assign materials digitally. They can review, grade, give feedback digitally to students. Students can also set up accounts. again, using Google. So if you are like my school and all students have a Google email account already, this is a very nice thing. It makes it easy, not another login they have to remember. They can view and complete content digitally. They can view their digital feedback and their grades. They can watch videos associated with the content, and they can engage with digital simulations. Lots of good materials. Now, let's talk a little bit about how they align with the standards. We'll start with the next generation science standards. They have performance expectations, which are supported by three things: disciplinary core ideas, cross-cutting concepts, and science and engineering practices. The standards for physical science can be found in the following document, and they are grouped by disciplinary core idea. And I'm going to show you kind of what that looks like. So you have your performance expectations, your standards up above, telling you what you are expecting students to be able to do. What are they going to perform to show you? And then each performance expectation comes with a set of disciplinary core ideas, so the content, cross-cutting concepts, and then science and engineering practices that are going to help them understand and perform those performance expectations. And this is just a continuation of the ones for those standards that I showed you. So you can see a whole long list of standards, but not too many disciplinary core ideas. Similarly, the Nebraska College and Career Ready Standards for Science are built to contain one disciplinary core idea, one cross-cutting concept, and one science and engineering practice for every performance expectation. So it looks a little bit different. Instead of having a whole list of performance expectations that go with a list of DCIs, CCCs, and SEPs, we have one per. The standards for physical science can be found in the following document, again, grouped by DCI. And this is what that would look like. Here are the science and engineering practices, disciplinary core ideas, and cross-cutting concepts. So as you can see, again, not very many. A short list of disciplinary core ideas as a whole. And then when we look at each standard, you can see that they are laid out, like we said, to have one of each of those supplemental pieces inside the standard. So the disciplinary core idea is left in plain text, the cross-cutting concept is underlined, and whatever the science and engineering practices is listed in bold. The materials on the Concord Consortium were designed to align with the next generation science standards, not specifically with the Nebraska ones, which makes sense, right? Most curriculums are written for like California, Texas, and Florida, not for Nebraska. But the Nebraska science standards align very similarly with the next generation science standards. I'm going to show you both sets of standards so you can observe how similar they are in structure and implementation. So moving forward, as I talk about ways that the Concord Consortium has aligned their curriculum with NGSS, I'll try to draw attention if I notice there's any differences between NGSS and Nebraska standards. But if I don't show you a specific difference, you can assume the differences are minimal. So if the curriculum is aligned with NGSS, it would also be aligned with the Nebraska standards. So on the landing page for the interactions unit, like I showed you, each unit displays underneath it the standards covered by that specific unit. We looked at that. The following is a list of all the next generation science standards that are covered by the interactions units, and next to them, the associated Nebraska standards. So we can see here the similarities, right? Use mathematical representations of Newton's law of gravitation and Coulomb's law to describe and predict the gravitational electrostatic forces between objects. Use mathematical representations of Newton's law and gravitation and Coulomb's law to describe and predict the gravitational and electrostatic forces between objects. So they are very similar, not very different. The only place I found really a major difference is that this performance expectation for NGSS really is a combination of two separate ones on the Nebraska College and Career Ready Standards for Science. just pause on each slide so you can stop the video and look at these if you want to look at them in more depth. I understand if you don't want to just totally take my word that they are lining up, but they do line up extremely well. In terms of alignment to disciplinary core ideas, cross-cutting concepts, and science and engineering practices, we have to look at the provided teacher's guides. As we looked at earlier, at the start of each activity, there's a table that's provided that shows the specific disciplinary core ideas, cross-cutting concepts, and science and engineering practices associated with each of the learning goals or performance expectations covered in that activity. What we didn't precisely look at is that they also include some cross-cutting concepts and science and engineering practices that are not specifically attached to that specific performance expectation, but they are obviously from the standards. So we have multiple cross-cutting concepts in science and engineering practices, which is wonderful to get additional ones in there and not just necessarily the ones covered by those standards. So here's an example of what that looks like. You've got your disciplinary core idea, your cross-cutting concept, and your science and engineering practice that is associated with this performance expectation. Listing standards covered is one thing, but we need evidence provided that the practices behind the standards are also being implemented, because it's all well and good. Anybody can slap a standard on the top of a worksheet and say, there it is, we covered it. But if what is done in the activity isn't actually backing that up, then we have a problem. Okay? To this end, we're going to look at the EQUIP, Educators Evaluating the Quality of Instructional Products rubric, which was a tool devised specifically for evaluating instructional materials to see if they align with next generation science standards. I'm going to review some points of the version of this rubric that I filled out for the Concord Consortium, but you can also find the full rubric that I filled out at the following link if you want to look at it in its entirety. So, explaining phenomenon/designing solutions. This is one of the criteria that needs to be met. Making sense of phenomena and or designing solutions to a problem drives student learning. So this is the expectation that we want to see. How the Concord Consortium does it. Every unit has driving questions related to an observable phenomenon. Each activity within a unit has a related set of questions. They help capture student attention and curiosity. Standards connection example. For Unit 1, Part 1, the question is, why do some clothes stick together when they come out of the dryer? This directly connects to the performance expectation for this unit, which is to use mathematical representations of Newton's law of gravitation and Coulomb's law to describe and predict the gravitational and electrostatic forces between objects, since it allows students to begin building the underlying knowledge of what causes electrostatic forces. So this phenomenon of having clothes stick together is directly connected to understanding electrostatic forces, and that phenomenon is what is driving student learning. So we're looking at that phenomenon, we're trying to figure out and answer that question, solve that problem, and that is what is driving forward our understanding of electrostatic forces. So this very much aligns with the standards. Another criteria from the rubric. Integrating the three dimensions. Student sense-making of phenomenon and or designing of solutions requires student performance that integrates elements of the SEPs, CCCs, and DCIs. How the Concord Consortium does it. Every activity, discussion, and experiments have specific SEPs, CCCs, and DCIs associated with them. The questions asked of students and the tasks designed for them specifically require them to make use of these to understand the phenomenon. Standards connection example. In the first activity from Unit 1, Part 1, the following can be found. The disciplinary core idea for this one is that the structure and interactions of matter at the bulk scale are determined by electrical forces within and between atoms. So that's the core idea we want students to understand. Students are then asked to interact with several charged and neutral items, and they develop models to explain those interactions. Cross-cutting concept for this performance expectation is to observe patterns in systems and cite patterns as empirical evidence for causality in supporting the explanations of phenomena. So when students collect data about the interactions they had with charged and neutral items, and then they use that data as evidence to defend their models, they are doing this. They are observing patterns in their own data, and they're using it to back up their model for why this phenomenon happens. And then the SEP is to use mathematical representations of phenomenon to describe explanations. This one doesn't connect maybe as well as you might like it to, but that's simply because they chose not to introduce the specific mathematical representation in this unit. So they did not introduce Coulomb's law or Newton's law of universal gravitation. And that's because they want students to understand what electrostatic forces are and what gravitational forces are before they ask them to apply a formula, because otherwise students fall into this trap of simply applying a formula, but they don't really understand what that formula is saying. So the idea is that these activities are to build understanding of those underlying concepts, and then in later units, they do introduce these mathematical representations. So it is still supporting that SEP, even though we don't see the actual mathematical representation show up. Unit coherence. The next criteria is that lessons need to fit together to target a set of performance expectations. How the Concord Consortium does it: every individual activity, lesson, and unit builds on the previous one to help students process incrementally towards understanding of these topics. The example: the pattern in incremental building can be seen in the driving questions for each of the activities in the first investigation. So if we look at these driving questions, we can see how they are building on each other. We start with what are some examples of things that stick together and things that don't. Then once we understand that some things stick together and some things don't, we develop some patterns about why some things stick together and some things don't. What are some patterns? So now we're not just looking at different things, but we're trying to figure out why. What is the data? Why are some things sticking together and not? What effect do charged objects have on uncharged objects? So now that we understand that charged objects stick together and don't stick together, now we want to see how those affect things that aren't charged. Then we want to know how we know if something is either positively or negatively charged. And finally, how does a charge affect its interactions with a neutral object? So each of these is building on the previous one. And if you look in the teacher's guided materials as well, you'll see that at the end of each activity, they have a series of questions that they recommend you ask students to connect what they are learning now with what they are going to be learning in the next unit. And then at the beginning of the activity, what they are working with previously that now is going to apply to what they're working with today. So they really are trying to draw these connections between the different activities and units. And then finally, relevance and authenticity engages students in authentic and meaningful scenarios that reflect the practice of science and engineering as experienced in the real world. How the Concord Consortium does it: the phenomenon they select are meant to serve two purposes. They need to be readily experienceable, aka not something that is difficult for a student to experience either in class, hands-on, or using a simulation. Needs to be something that they have access to, so it's real and it's in front of them. And then they should be common enough that students may have some experience with them. So an example of this, the phenomenon selected is static electricity experienced through clothing sticking together. So it's very easy to demonstrate static electricity in a classroom. This unit does it with the use of balloons, wool, satin, tape, glass rods, and carbon rods, rubbing various objects on each other and experiencing that. So it's very easy to do hands-on. And most students have had experience with their clothes sticking together, maybe when they take their jacket off in the winter, or when they take their clothes out of the dryer, or when they're sorting through their laundry, clothes sticks together. So most students should have had an experience, so it feels authentic to them. These are not the only criteria from the EQUIP rubric that show up and are connected to the standards in the curriculum. These are just 4 that I thought were big and obvious and important. If you want to go back and click that link, you can see that there are many more criteria met. Now let's jump into neuroscience-based practices. The first one I want to talk about is depth over breadth. The list of disciplinary core ideas presented in both sets of standards are significantly shorter than I remembered, and it just reminds me of the push to switch to this newer model, which encourages a depth of knowledge or understanding over a breadth of knowledge, rote memory effect. A similar point is discussed in Upgrade Your Teaching: Understanding by Design Meets Neuroscience. In Chapter 2, the authors explain that rote memory does not transfer well to new contexts. Deeper understanding of core general ideas are significantly more applicable to new situations. In practice, for me, this means that looking at the DCIs and standards and really digging for what the core information is going to help focus my curriculum. I'm going to take that and really give students the opportunity to make sense of what they're seeing and being asked to understand. I can focus in on those DCIs, on the performance expectations, and not worry about completing a whole textbook, but really focus in. Next, we have transfer. This is related to that previous one. If my students can list for me the steps of the scientific method, but they can't plan and execute a proper experimental research project, what does knowing those steps profit them? Discrete knowledge is only as powerful as its application allows. As Matighi and Willis put it, students should develop know-how, not just knowledge. I need to scaffold in opportunities for my students to engage in meaning-making activities with information, helping to strengthen those neural pathways and make application easier. I can do this through the use of summaries and comparisons, categorization, symbols, models, lots of other methods. While initially I can model this for my students, eventually they're going to need to take control of this process for themselves if they're going to be able to learn on their own later. This style of scaffolding is built into the units of the Concord Consortium, with students eventually designing and planning their own experiments to make sense of phenomenon. Student-driven goals. Our brains work at their best when motivated by goals. For students, these goals are best when they are clear, relevant, achievable, and when they can see progress towards them. In my classroom, I do present learning objectives to my students. What this curriculum does, however, is brings these goals to life for the students. When the students can see the relevance of a goal, or even just be fascinated by them, they are much more likely to pursue understanding those goals. So taking these relevant real-world situations and allowing students to see how their knowledge can be applied to them is going to help those students really focus in. Pre-assessment. In order for the brain to learn information, it must attach it to information that is already stored inside the brain. As educators, then, we need to figure out what our students have already in their brains that can be built upon. This curriculum has built-in pre-assessments designed to give all kinds of information about where students are coming from. Additionally, the driving questions, when posted to the classroom wall, can serve as a little bit of a KWL chart to track student understanding as we progress. These tools can also serve as hooks to grab student interest and engage them with the content that is at hand. So I look forward to using and trying these pre-assessments, as I think there's a lot of knowledge in there that helps you understand where students are at academically, where they're at with the concepts, what you need to do most for each student to help move them forward. Differentiation. If students feel that a goal is too difficult or that it's unachievable for them, their brains are not likely to spare the energy for them to work on it. Pre- and ongoing assessments, like the ones built into this curriculum, give teachers an opportunity to tailor tasks to students to make them achievable. Without compromising on the outcome of a task, while we want them to show us they've learned, we can modify aspects of tasks to be achievable for students from all walks of life. This puts students up for success and encourages the building of growth mindsets in our students. Let's talk briefly about current practices, things that I'm already doing. So I already post my objectives or my goals for the day every day on the wall in the classroom, so students have clear goals that they know they are working towards. So that is not going to be new to students. I already give students feedback through formative assessment. So we do several checks for understanding over the course of a chapter, where I can see how they're progressing, what they're understanding, what they're not understanding. I can give feedback. I can tell if we need to go back as a whole class and redo a lesson, or if we didn't understand what the purpose of a lab was, we can go back and hit that again. So there are lots of opportunities for formative assessment for students in my classroom already. And then finally, we do already do some project-based learning. So students are going to be familiar with the concept of here's a problem, and we're going to work towards this problem, and this problem is going to be what is driving our learning. We do a very cool project based around the melting point of ice, where students are expected to design experiments to test which substances will melt ice and keep it melted the longest. And they have to prepare reports for the Nebraska Department of Transportation, and they have to do all of these things. And over the course of that unit, they discover what causes substances dissolved in water to change its melting point or its freezing point, and why. So they learn a lot about particle interactions in that. So we do some project-based learning. That's not unfamiliar to them. What would need to change for me to implement? I would need a change in organization. Right now, I feel like I fall into that trap of coverage. I need to worry less about covering every section of the textbook, and I really need to dig into those core concepts, those DCIs and the performance expectations, and look for a sequence that's going to best fit for student understanding, and worry less about, did I hit every chapter in this textbook? Appropriate use of pre-assessment. I already mentioned pre-assessment briefly. So not only do I need to give the pre-assessment and make the KWL charts, but I need to spend time with the data that they provide. Allow those insights to make their way into my instruction so I can see where students are starting from, what helps they need along the way, all of that. Then conscious differentiation. Looking through all the many opportunities for formative assessment, and I want to use them wisely to help set achievable goals for students. So I set goals for students, but I don't involve them in the process as much as I should, and I don't always make those goals achievable for each individual student. So really taking time to use all of the tools provided to make sure that I'm setting each student up for success. Hook. Be conscious of the ways that I can use this content to engage students. It's great to have the phenomenon to use, but if I'm not actively trying to engage students with it, some of them are still not going to be interested in it. Some of them are going to go, so what? Clothes stick together. Who cares about that? So helping them see the value and the connection. And then meaning making. Use chances for self-evaluation and feedback to help students make meaning of the material. There's lots of chances for feedback in this, but there's also several opportunities for students to self-reflect and to make changes to their models or look back over their data and see if there's something that they missed in their data. Look at those patterns again. Try to make predictions again and improve their predictions. And I want to make a conscious effort to guide students through that at first, hopefully, and take the training wheels off as we work through it, and they can take some of that meaning making on for themselves, but really a conscious effort towards this meaning making. Less worry about rote memory, can they answer a multiple choice question, more about, do they really understand this content? And here are my references. I'll pause just slightly on each page so that you can pause the video if you need to look at any of them.